Hi guys, today's topic is about database system architecture. It's a comprehensive guide to understand how database systems are internally structured and managed. This presentation will also explore architectures, components, and their real-world applications. So, first introduction. A database system is a software that manages data with high efficiency and security. So, it will manage the data very secure manner. So next, the DBMS architectures defines how data, users, and process interact. It ensures abstraction, performance, and maintainability. Architecture influences scalability, response time, and complexity. Commonly includes layers and modules. Each layer performs distinct roles, enable system transparency and independence. A good architecture supports growth and evaluations of systems. So database architecture overview. Architecture is a blueprint of how components interact. It promotes modularity and separation of concerns. It supports abstractions. User interact without knowing internals. Provides flexibility to scale components. It helps in enforcing security. Simplifies data access and management. Key types: 1 tier, 2 tier, 3 tier architecture. Foundation of any enterprise grade system. 1 tier architecture. All components reside in single machine. Example: Microsoft Access SQLite. Simple setup for personal or academic use. Limited security and scalability. Tight coupling of UI, business logic, and DB. Direct access to DB files. Ideal rapid prototyping. Not suitable for network environment. So next, two-tier architecture. It divides client and database layers. So the UI and business logic in on the client and DB bus on the server. The communication will be via APIs or SQL. For example, MySQL client server model, ODBC or JDBC. It is better than one tier in terms of data control. So the data control is very main advantage here, and its drawbacks is limited scalability and security. It is suitable for LAN environment. Next, three-tier architecture. It adds a middle layer, that is application layer. So the layers are presentation, business logic, and data. Each layer can be managed and scaled independently. It enhances security by isolating DB layer, common in web apps. Example: Java EE and .NET. It supports load balancing and caching. It promotes reusability and maintainability. In real world, it is used in banking and e-commerce. Next, three-tier architecture diagram. First, client, browser or mobile app. Middle tier, app server or API layer. Data tier, DBMS. Layers interact through defined interfaces. Decouples front-end and data management. It reduces client-side load and enables distributed deployment. Each layer can evolve independently. The components of DBMS architecture. So the components are DBMS engine. It is a core processor for data operations. The query processor. It processes and optimizes queries. Storage manager manages data storage. Transaction manager, it ensures consistency. Catalog manager maintains metadata. Buffer manager, who manages in-memory data. The authorization manager control accesses. Log manager record all operations for recovery. So the DBMS engine, it orchestrates query execution and transaction processing. It converts high-level queries into low-level instructions. The interfaces with storage manager. It supports concurrency control. It maintains integrity and security constraints. It coordinates with other manager, log or transaction. It ensures system performance. It acts as a execution core of DBMS. Next, query processor. It analyzes and converts SQL queries. DBML compiler passes user queries as query optimizer. It generates efficient execution plans. Execution engine executes instructions step by step. Cost-based estimation using historical indexes. Avoids full scans by using indexes. It uses algebraic transformations. It ensures faster query responses. Next, query processor diagram. So for the flow will be the SQLite, the parser, then the rewrite rules, optimizer, then execution plan, then engine. Query plans can vary greatly in performance. It visualize helps understand optimization paths. Common tools are explain, visual explain plans. Next, storage manage. It handles how data is physically stored. It works with file system and disk manager. Manages indexes. Example b plus tree hash tree. Next, it maintains free space and allocations. It includes buffer pool and cache strategies. It supports compression and encryption. It is responsible for data integrity. Interfaces directly with physical storage. Next, transaction manager. It controls database transaction as it that is atomicity, consistency, isolations, durability. It uses logs, timestamps, and serializability. It prevents issues, lost updates, and dirty reads. It handles concurrency with minimal conflicts. Recovery manager integrated for failures. It ensures next is the catalog manager. It manages the system catalog, that is metadata. It is used to store schema, tables, indexes, and views. It tracks user permissions and roles. It enables data discovery and introspection. It's required for query planning. It often queried by system tools. Maintains referential integrity info. It acts as the knowledge base of DBMS. Next, data independence. It is a logical data independence. It changes logical section without affecting applications. Next, physical data independence. It changes internal schema, example indexes, without changing logical schema. So important for long-term system evaluation. It encourages abstraction. It reduces cost of changes. It allows admin optimization without breaking code. One of the key goal of DBMS designs. Next, level of DBMS architecture. So there are internal level, conceptual level, external level. So internal level, physical data storage. Then conceptual level, logical data structure. Next, external level, individual users views. It promotes data abstraction. It enables security via custom views. Next, it shields user from security system complexity. Next, it helps maintain consistency across users. And the schema architecture. Three schema architecture by ANSI and SPARCY. External schema, user specifies representations. Conceptual schema, unified logical views of all data. Internal schema, details of physical storage. It promotes flexibility and independence. Standards for modern DBMS design. Next, schema architecture diagram. Then, first the external view, then conceptual view, and the internal view. The arrows indicate data transposition. So, first, the external view will transfer the data to conceptual view. Then, it transform the data to the internal view. It is useful for teaching data abstraction. It often shows an three-layer pyramid or stack. The data flow and DBMS steps. The query is submitted by user, then it is passed by query processor. Execution plan created. The data fetched from storage. The result written. Each component plays a role. Ensures correct, efficient data access, logging and buffering used during process. Real-time system often add extra monitoring layer. Centralized versus distributed database. Centralized database. Single location storage. Easier management. Risk of single point failure. Distributed DBMS. Multiple nodes or geographics. Improved fault tolerance. Complex synchronization. It is used in global subs. Example Google Scanner. Next, trade-offs. Consistency versus availability. CAP theorem. Next, client server architecture. Server stores and manages database. The client queries via network protocols, common in LAN, cloud, database, and web apps. For example, PostgreSQL Oracle promotes centralized control, can integrate with load balancers. Its security via SSL and authentication allows remote access and control. Next, summary. The database system architecture is vital for building scalable systems. Components will work together for storage, access, and security. Three-tier and client-server model dominate modern systems. Query optimization and storage management are core areas. Distributed systems add scalability and complexity. Understanding architecture aids in better system design, supports maintainability, flexibility, and security, enables data driven innovation. So, thank you. Thank you for watching this video.